Physics, mechanics, and okay. So we have an object of 10 kilograms, which is probably fairly irrelevant, and it gives us some velocity function here. So the velocity is 2t plus 3t squared. We know that the velocity is nonlinear, so it's going to require calculus. Two choices. Choice one, how far does the object travel? Really, all you're doing is saying that delta x is the accumulation of velocity over time. So we're just integrating over that for the first 10 seconds. I don't actually know why I didn't do that. I went a little old school and I just actually found the position function itself. And so I integrated velocity and got t squared plus t cubed plus some c. The c is completely irrelevant because it's the initial position. How far you move from 0 seconds to 10 seconds, that actually is independent of where you started. Right? We're just looking at the distance you traveled during that time period. So I guess if I did this key again, I would have just said that delta x was the integral of v dt, and you would have gotten the same thing. Either way, once you have a nonlinear velocity, you must do calculus. Right? Instantaneous net force, well, you want the instantaneous force, you got to find the acceleration. So we're really just taking the derivative of velocity to find acceleration, and then multiplying by the mass to find the force. And again, we want the force at a moment, so we just need to find the acceleration at 2 and multiply by the mass. How much work done? So we're going to the work energy theorem. Work equals the change in kinetic energy. So you want to find the work done from 0 to 1. Well, just figure out how fast it's moving at 0, which is 0, and figure out the velocity at 1 second, which is 5, and then you can figure out the kinetic energy gained. The work done is the increase of kinetic energy. All right, this one, we're looking at displacement. Displacement is a vector. And so when we start here and we go and somebody walks x, someone walks all the way around to y, and someone walks all the way around to z. The person z, they walked a bigger distance, but their displacement is 0 because they're right where they started. Person x walked the least distance, but does have the greatest displacement based on looking at the red arrow. Again, displacement is a vector. Okay, so they give us accelerations in two different dimensions. So just look at in the x direction and the y direction. So they both have no initial velocity and no initial position. So both the y and the x both have that same form. Y equals 1/2 at squared, x equals 1/2 at squared. And so it wants to know what the x-coordinate is when the y-coordinate is 12. So just set y equal to 12 with an acceleration of 1 and solve for the time. The time it would take is the square root of 24. Then plug that time into the x equation, 1/2 at squared, using an acceleration of 2 in the x direction. So 24, square root of 24 squared is 24, half and the 2 cancel, and you get 24. Again, you're really just using the basic kinematic equations. No initial position, no initial velocity, and you're finding a certain position x related to a certain position of y. All right, this one, it says the speed of an object is increasing at a constant rate. That is telling you that the acceleration is constant. Again, speed increasing at a constant rate. The acceleration is constant, thus the force causing that acceleration must be constant. Right? So we got that. The force must be constant, and again, not 0. So we got a frictionless surface, and what we're doing is we're pushing this. So we're pushing this, and they tell us we're accelerating at 4. And we know it's 6 kilograms. Again, you don't know whether it's 2 boxes, 1 box, 5 boxes. You're just pushing both boxes. So you're pushing 6 kilograms at 4 meters per second squared. So you must be pushing at 24. Now, if we want to know this internal force, then we can look at just one of the boxes. And it doesn't matter which box we look at. It looks like I looked at box X. Looking just at box X, you're pushing it with 24. We don't know what box Y is pushing back at. Again, back Y it's negative. And then it's just the mass 2, because we're just looking at that box accelerating at 4. And so if you solve this for Fy, you're going to get 16. And remember, Fy is pushing back at 16, just like Fx is pushing y to the right at 16. And again, we probably could have done that even easier without any of this. And if we just think, okay, wait, the box y is accelerating at 4 and it's 4 kilograms, so it's got to have a net force of 16. Boom, we're done. Again, because we know that box X is pushing box Y at 16, thus box Y is pushing X at 16 to the left based on Newton's third law. So we actually could have done this question much faster. All right, a hoop is rolling, and we want to look at translational kinetic energy. Remember, that's old school, 1/2 mv squared, versus rotational kinetic energy, which is 1/2 I omega squared. We know that omega is V over R, and so if you plug in for a hoop, it ends up that the 1/2 mv squared versus the 1/2 I omega squared is actually identical. And so the ratio is 1. All right, here's the parallel axis theorem. So we're taking a sphere and we're rotating it, and we want to take the rotational inertia about an axis tangent to the sphere. So we're moving the parallel axis theorem. So here's our sphere, and we're moving the pivot so it's on the edge of the sphere. So the parallel axis theorem says take the center mass plus an md squared, and we moved it up to a position r away. And so we're just increasing the moment of inertia of that guy. All the following quantities are vectors except energy. Energy is not a vector. Torque is a vector. Angular momentum is a vector. Angular velocity, this spin, you could be spinning clockwise or counterclockwise. It's much different. Centripetal acceleration, again, is a vector. I know it's pointed inward, but it's still an acceleration. It's still caused by a force. It is a vector. Energy is not. All right, we got this raft. Its velocity this way is constant, but it's got a force vertically, which will make it accelerate vertically, and so it's going to have that sort of position graph. Horizontally is going to be chilling. It's still going to be going right, but it's going to be accelerating vertically, so it's going to be a parabolic curve upward. So we have some velocity as a function of time, which tells us we need to do calculus, and we want to find the distance traveled. We just integrate from 1 to 2. Again, this is a definite integral. This is the integral, and then we evaluate it from 1 to 2. We're looking at the gravitational attraction of two masses. They each have a mass of 3. They're 6 apart, so it's gmm over r. Remember, g is 6.67 times 10 to the negative 11th. This question actually won't be asked anymore. This was something they made you do without a calculator, and so you just had to do this order of magnitude. Basically, you're just saying that 3 times 3 is 9. 9 over 36 is just like a fourth. A fourth and a 6 kind of cancel, and you're left with that 10 to the negative 11th in terms of the order of magnitude. It's pretty much something close to 10 to the negative 11th, which now you have your calculator for all of these, so this question would probably be more of a double, triple question rather than a numeric question. All right, we got a satellite of mass m in circular orbit. We know we can derive these really quick. The escape velocity, you can use energy to derive, and orbital velocity, you can use forces in circular motion to derive. And the ratio of those things ends up just being radical 2. Escape velocity is the square root of 2 gm over r, or orbital velocity is the square root of gm over r. Okay, this is a double triple question. This is the period formula for a mass on a spring oscillating back and forth, whoom, 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 whoom. And if you double k, k's in the denominator, it's going to make the new period 1 over the square root of 2, right? You're going to make it smaller by the square root of 2, so you're going to divide by it. This is still similar harmonic motion, and we want to find which of the following is a possible expression for the potential energy as a function of time. Okay, so we know potential energy for a spring is 1/2 kx squared. So 1/2 k and then x. Well, x is this guy. We usually use cosine, but it doesn't matter. You can use sine. We usually use omega t, but again, we know omega is 2 pi f. So this is our answer. 1/2 k x squared. If you square x, you're going to get an a squared, and you're going to get a trig function squared. 17, right? The work done in stopping this wheel from spinning, you're going to think work energy theorem. The work done is the change in kinetic energy. The kinetic energy is the rotational kinetic energy that this wheel the wheel has. So it's going to be a negative because you're stopping it, and then it's a 1/2 I omega squared. They gave you revolutions per second. That's frequency. So you got to multiply by 2 pi to get it to omega, and then just multiply that out. A uniform beam is attached, and so we got our classic hanging sign torque equation. We know that torques are forces with lever arms. So in this case, the torques are balanced. This is the torque that the cable causes, the tension, the length, sine theta. And then the torque that the beam causes, the weight, meaning mg, and then the lever arm, L over 2. And there's no angle there because this is perpendicular to that. Set them equal to each other, solve. 19. Okay, so we're looking at the speed of the center. This one actually tricked me when I was doing the key, because normally we have some arrow coming in and hitting this thing, and it's going to cause this thing to rotate, which is true. So everything I wrote down here is true. It's just not helpful in the question. Of course, we are conserving angular momentum, and that would give us maybe how fast it's going to be rotating afterwards. It just happens that that's not what the question asks. I didn't actually read the question before I started writing. It actually just wants to know the speed of the center of mass. So that's just this. That's just regular old linear momentum, because linear momentum is also conserved because this thing isn't bolted down. Since it's not bolted down, there's no external force, and so we can conserve regular momentum as well. Again, I thought it would cause a rotation, which it does, and I figured it was this, but it actually just wants to know linear momentum. So just conserve linear momentum and then solve for the velocity afterwards, and you get that. Okay, so you get this situation. These are the same masses, and it's going at 3, and then 2, and then 2, and then 3. You're like, oh, well, of course momentum is conserved because it's collision, but it looks like kinetic energy also must be conserved, considering they have the same velocities and masses afterwards that they did before. They just kind of switched to rho. So the kinetic energy here is clearly the same as the kinetic energy here, and so it must be elastic because kinetic energy is also conserved. Momentum, clearly conserved because momentum is conserved in all collisions. All right, we got this box, it's moving, and it slides and comes to a stop. Well, if it comes to a stop, that must mean that the work done by friction, the heat created by friction, took away all the kinetic energy. So just set those things equal to each other and solve. The frictional forces on the box is to the left, which means the box actually does apply a force to the floor to the right. That's Newton's third law. We don't really care about the floor. It's bolted down or glued down or nailed down, so it doesn't actually move, but there is a force. If the floor produces a force on the box must also produce a force on the floor. Okay, we've seen this before. This is the classic. I'm going to pull a box across the ground at an angle. So in the x direction, this is what we've got. And again, it is constant speed, which is why I put the accelerations to 0. And then in the y direction, I'm pulling up. The normal force is up, and mg is down. I'm going to use the bottom equation to solve for the normal force. There's your normal force. And then there's your equation of motion. Fa cosine theta minus mu times the normal force equals 0. And then you solve for mu, and you get that. All right, this one, you can go through the long way, and you can really look at each one of these things. You can look at the fact that there are 4 ropes pulling down and 2 up. They're going to balance. Or you can just think, dude, it's 4 ropes versus 2 ropes. They're all supporting the weight. And so the pulley is going to support half of the weight. If the tension throughout the rope is uniform, what is the reading on the scale? And again, the scale has 2 ropes here. So I guess we can really ignore those 4. It's just there are 2 ropes here supporting all the weight. It's going to read half. This one is tricky. Okay, so this one has a little special right triangles and then a little physics. The physics says this. The center of mass of the board can't move. Again, no external force. There's no friction here. If there was friction here, everything would be different and harder because this thing might just like fall down here and kind of pivot on this spot. But there's no friction, so it can't pivot here. That will actually move to the right as this thing falls. This position right here, that guy, that falls straight down. And so you think about, where is the right end located at the beginning? Well, think about it. This is a special right triangle. This is L over 2, this distance. Oh, it's not going to let me highlight a bunch. This is L over 2, the hypotenuse. And so this is half, considering it's a special right triangle, right? 1, radical 3, 2. So if this is L over 2, this is L over 4. When it falls, though, now the center of mass of the board is here, and it stretches out to L over 2. Thus, the end of the board went from L over 4 all the way out to L over 2. So the end of the board is actually moved L over 4. A lot going on there. But again, the principle is that the center of mass can't move. The center of the board has to drop straight down. Thus, the right slides out. When it's laying flat on the ground, it's at a distance L over 2, and it was at a distance L over 4. So it's actually moved that difference. This is a double, triple question, right? This is, you're letting energy, mgh, as it falls through, go to kinetic energy. If you double the distance it falls, you've increased v by radical 2. Doubling this increases this by square root of 2 because of the quadratic relationship. This is a calculus question, right? This is giving you the velocity, some negative exponential, and you take the derivative, right? This is what you get if you just flat out take the derivative of v naught e to the negative beta t. Remember, the derivative of e to the u is e to the u times u prime. So you end up getting a negative b here in front. And you're like, wait a second, that's not the answer. This would make sense if this is an answer, but it's not. They redo and put a as a function of v. But notice, this term right here, that piece in red, that is just v. So a equals negative bv. So they're a little tricky. They make you do like a little substitution in there. This is classic nonlinear spring. They give you a force, just integrate it to find the potential energy stored. Again, this is a non-Hooke's law spring. All right, so they're telling you you're doing this thing. You're letting this pendulum go back and forth, and it says, well, what would contribute to the most error? And you're like, hey, dude, this. We know we can only use the equation, it's only good for small angles. If you take that pendulum all the way up and release it from horizontal, it is not going to be good, right? You are introducing a ton of error because we know this equation is only true under the small angle approximation. All right, you go to a deep mine, gravity is going to get less. You can think about that. Right, there's our Earth. Once you get down in here, you actually have way less Earth even tugging you, and you're closer to that center. The outside Earth would no longer tug because it would be symmetrically tugging you. Some would be tugging you out and some would be tugging you in. Once you're actually down, only the Earth that's inside of you is actually pulling you, and you're closer. So less Earth and closer, the weight of the person is less than at the surface. Okay, this is kind of a twist on one of Kepler's laws. So this is actually looking at R in terms of omega. So do the same thing we always do. F equals ma. The force of gravity is gmm over r, and instead of doing v squared over r, now let's do omega squared r, and so we can just solve this in terms of r, right? Pop the r over there, divide by this, and we can get r as a function of omega. Usually, we get like orbital velocity with v, and we do the same thing. We just put v squared over r, but in this case, they wanted r compared to omega, so slap in omega squared r instead. All right, this guy, so we got this. When we release this thing, this one's going to go to the right at half the velocity that this one goes to the left. However, think about the center of mass. The center of mass cannot move unless there's an external force. Well, there's no external force. There's a force on this to the right, which is the same as the force on this to the left. And so momentum for this system is conserved. I get it. This one gets momentum right. This one gets momentum left. This moves small. This moves bigger. But as far as the center of mass, it stays right in the center. Nothing actually will change in the center of mass. No change in momentum, no force, no change for the center. And actually, if you wanted to, you could just give these numbers and make this 2 kilograms, 1 kilogram, make this one go 1 meters per second this way and 2 meters per second that way, and use the center mass formula. And you can show that the center of mass of the system at any moment in time, at 1 second, 2 seconds, 3 seconds, will always be at the origin. And again, we can show that in class if you needed to. All right, this is all about impulse. The impulse is the change in velocity. Velocity is a vector. So this one going 15 this way and then 10 that way, that's a change of 25. So the change in velocity is 25. So the impulse is the mass times the change in velocity equals some average force divided by that time to then find what the force would be. How does the magnitude of the average force exerted by the ball compare? Oh, Newton's third law, right? The ball and the racket and the ball, same thing. The racket applies the force to the ball, but the ball applies the same force to the racket in equal and opposite directions, right? There's almost always some Newton law question on the multiple choice. And the last one, this is an angular momentum thing. This is a collision. I think this actually was a problem we did in class where a guy runs, jumps on a merry-go-round. The merry-go-round is already spinning, and it's just going to make it spin even faster. So conserve angular momentum. This is the angular momentum, right? mv cross r. And then this is the other version of angular momentum, which is I omega. They both have angular momentum at the beginning. The disk is spinning. The child is running. They jump, they hang on. This is the new moment of inertia, and then they're going to be spinning faster. So then just divide, and we get the actual angular momentum of it afterwards. Okay, that was 2013 AP Mechanics video. Hopefully that helps you out.